Imagine if you had a ball and you decided to swing it around in a circle like this. And the velocity of this ball as it travels around in this circular path doesn't change. Let's say it's whatever, 5 meters per second. The magnitude of the velocity is unchanging. However, the object is technically always accelerating. How? That sounds weird, right? When you have an object moving in a circular path like this, the direction is always changing continuously at every moment. And according to Newton's first law, a change in direction counts as acceleration. So even if the magnitude of the velocity is the same, it's always moving at this same speed, the direction is changing. So technically this object is always accelerating. Now imagine you have an object like this and it's traveling in this circular path. After a certain amount of time, it moves here. The vectors look like this, and they're always tangential to the circle curve in this kind of circular motion. Now, the formula for centripetal acceleration, there's a bunch of math behind it, just like there is with every other formula. I'm not going to go through it, but if you did go through it, you would end up subtracting these two vectors. And when you subtract these two vectors graphically, they look like this. This blue vector is the result. This blue vector here is very special because it's always pointing toward the center, always. That is centripetal acceleration. The reason why it moves in a circle is because it's always accelerating toward the center. The formula for centripetal acceleration, by the way, I'll spell out centripetal right here. The formula, we'll label it as AC. It's equal to velocity squared divided by radius. Radius is, as you know, the length here. Now here's something that you should keep in mind as you solve circular motion problems. It makes it much more intuitive. The more velocity your object has, so the faster it's going, the more centripetal acceleration. So the faster it changes direction. The larger the radius, so this, the less centripetal acceleration your object will have. In uniform circular motion, so when the velocity is constant throughout, the acceleration, the centripetal acceleration is always perpendicular to the velocity, as you can see here. So it's always looking something like this as you fly around the circle. Let me teach you about time and frequency for circular motion. Now, if you study trig waves like sine and cosine, this might remind you of that. The formula for time is t equals 1 over f. F is frequency. So, for example, the frequency of your objects is 4 revolutions per second. So it spins around 4 times every second. Then your time would be equal to 1 over 4, which is 0.25 seconds. The formula for velocity is this, which I'll give you here. Now, as you know, velocity is distance over time, which means that we can substitute in our values. The distance is 2 pi r, because that is the circumference of a circle. The time, as we know, is t. Let's run this through an example, and if you want all those formulas in one place, there's a free cheat sheet I made for myself, which I'm sharing with you. You can get it for free in the description. Let's say you have a ball, and your ball is 300 grams. You've attached it to the end of a rope, which is 2 meters long. You decided to start swinging it in a circle for whatever reason, and it makes 2 revolutions per second. What is the centripetal acceleration? Which is this, remember? Well, let's use our new formulas. We're looking for the centripetal acceleration. So the centripetal acceleration is given by velocity squared over radius. But we don't have velocity. Velocity is circumference over time, but we don't have time. So time is 1 over f. Well, now we're ready to solve. We have the frequency. The frequency is 2 because it spins twice per second. That means time is equal to 1 seconds. And velocity is 2 pi times 2 meters, the radius, divided by our new time value, so 0.5. Chuck this into a calculator, you get roughly 25.132 meters per second. Now let's use the centripetal acceleration formula. which is velocity squared, so this number squared, divided by radius, which is 2. And when you solve that, you get roughly 315 meters per second squared. That's the centripetal acceleration of our ball. Here's an example that I'll let you do yourself. So imagine you're designing a delivery drone, you're a drone engineer, and your drone, which we'll label with this circle, it's delivering a payload of 2 kilos. It's a 2 kilo item. But when you deploy your drone, it's very windy and the turbulence means it starts swinging in a circle. It swings at 2 revs per second, so 2 revolutions per second. And the cable of the drone is 1.8 meters to the edge, like that. What is the centripetal acceleration? Go ahead, pause the video, try and find it. Now I'm going to solve it together with you. First, let's find the period, so how long it takes to travel in one circle. That would be t is 1 over f, which is 1 over 2. 2 revolutions. Now let's find the velocity, which is 2 pi r over time. This is 2 pi times 1.8 meters, the radius, divided by time, so 0.5 seconds, which we just solved for here. Now for centripetal acceleration, which is velocity squared over radius. This is about 22.6 squared, which is our answer from here, our velocity, divided by 1.8. And when you run this calculation, you get roughly 284 meters per second squared. That is the centripetal acceleration of this little thing here. Here's a fun one. Let's find the centripetal acceleration of the moon. So this falls under orbital mechanics, which is a really cool sounding topic. Say this is Earth, and you have the path of the moon. Now the moon here is about roughly 384,000 kilometers above Earth. The period, so how long one orbit takes, period is t, which is 27.3 days roughly. From this, are you able to find the centripetal acceleration? Let's solve this together. Now, when it comes to centripetal acceleration and you look at the formula, what do you need? What are we missing? Well, we have radius. We just need velocity. We don't even need to solve for time because we don't have that here. Let's go ahead and plug in our values. So as you know, velocity is circumference, so this, divided by time, which is this. Let's quickly convert days to seconds. There, that's our answers in seconds. So it takes this many seconds for the moon to travel around the Earth. Next, we have to convert this to meters, which is very simple. We just times 1,000, which means we just add 3 zeros. That's equal to 3.84 times 10 to the power 6 in scientific notation. Let's plug in our values and find velocity. So this would be this here and this here. These are some big numbers. I'm not going to write it all out, but just know that your tangential velocity is equal to 1020 meters per second. Now we're ready to find centripetal acceleration. Formula is AC is v squared over r. Put in this for v and put in this value for radius. When you plug in your values, you'll get roughly 0.00272 meters per second squared, which is in scientific notation 2.72 times 10 to the power 3 meters per second squared. Now this is a very small number, and you might be surprised because the moon, as you know, is moving very fast throughout space. The reason why this number is so small, even though the moon is so fast, because the centripetal acceleration of an object gets lower when the radius is bigger, which is what I was talking about earlier. See the radius? The moon is very far. Now that was the kinematics of circular motion. It was acceleration and velocity. But how about the dynamics of circular motion? So now we're going to count forces. When you have an object moving in a circle, we know that it's always accelerating. Newton's second law says that for an object to be accelerating, there has to be a net force acting on it in some way. So that means in circular movement, there's always a constant force being applied to keep it moving. Now, what is this net force? The magnitude of this net force, well, when we apply the second law in the radial direction basically just means the centripetal direction toward the center. Now look here, this here AC, that's centripetal acceleration. So here's a very important formula. This is the formula for centripetal force. Fc for centripetal is equal to mass times velocity squared over radius. And we took this from the formula for centripetal acceleration. This formula is also on the free cheat sheet, and we're going to be using it quite a lot. Now here's something interesting about centripetal force. There must always be another object applying the force. For example, when you're swinging a ball, you're pulling on the rope. Or when the moon spins around the earth, gravity is pulling it in. So centripetal force and circular motion doesn't come out of nowhere. And let's use the same diagram to explain a misconception. If you've ever swung something in a circle, like, the classic ball on a string example, you might feel a force pulling it out. You might feel something pulling it away, That would be centrifugal. But here's the thing. There is actually no force pulling it out. Even in this example of you pulling a ball on a string, when you pull on the string, the ball exerts a force back. That's what you're feeling. Because third law, every action has its equal and opposite reaction. If you want proof of this, and here's real life proof. When you swing a ball in a circle like this, and you swing it really, really fast, and you let go, what happens to the ball? It doesn't start flying off like that, because there's no outward force. It flies off instead like that. Here's a fun example to make use of the concepts we just learned. Let's say you're at a famous theme park and they have a very special ride. It's a super fast spinning roller coaster arm thing. And you sit on the end of it. Let's draw a diagram. Right. Here's the arm. And you sit here at the edge. Which we'll draw a circle for that. And it's a very, very fast spinning ride. It's spinning horizontally. Let's say that the mass of this thing at the end is 3.2 kilos. The radius is 0.8 meters, and it spins twice per second. What is the centripetal force acting on you? Let's draw the forces acting on an object. First one, we have gravity. And here's the force providing the centripetal acceleration. It is the mechanical arm that spins around, which is the tension. Let's find what we're missing. So the formula, if you remember, for centripetal force is Fc equals mv squared over r. We know the mass is 3.2 kilos. We know the radius is 0.8 meters. What are we missing? We need velocity squared. When you solve for velocity with the formula, so 2 pi times 0.8 meters, the radius, divided by 0.5 seconds, which is the period, you get somewhere around 10.05 meters per second. Plug this into the formula, you get Fc equals 3.2 kilos times 10 meters per second divided by 0.8 meters, the radius. This gives you 404 newtons of force. So the centripetal force is 404 newtons. When you're spinning around really fast, you're getting pulled toward the center with this many newtons. Now there's a second approach you could have taken. This centripetal force formula, right, mv squared over r, you can write it as m times centripetal acceleration. It's the same thing. So if you wanted to find centripetal acceleration separately, like this, then plug it in, that would give you the same answer. So it's just up to preference which formula you would like to remember. Now how about gravity? We didn't consider gravity here. In this example, gravity, if you went and solved it, would be only a few newtons. It would have a negligible effect on things like the force here and how fast it's moving. So we're not going to consider it in this problem because it's just not worth it. So we've done a lot of examples on horizontal movement. So swing a ball around you or the roller coaster. What about vertical movement? So let's draw a proper diagram for this. This problem is a lot of fun, and I think you might be able to relate to it. Imagine a child playing at the beach, and he fills a bucket up with water. And his bucket, let's draw it like this, he begins swinging it around in a circle, like this. Let's assume this motion is non-uniform, which means that at some points it'll be faster, and at some points it'll be slower. It's not constant. The child's arm, let's assume he's quite lanky. He has 2.3 meters long arm. And the bucket is filled with 750 grams of water. At this top point, at the peak of the path, how fast does he need to be swinging the bucket to keep the water in the bucket? So basically, to keep it moving. First, with free body diagram problems, we should label the forces. So we have gravity, and we have the tension of the handle, which is same here. We have gravity and the tension of the handle. Now the tension of the handle is the centripetal force. And the question is asking us, what's the minimum speed? The minimum speed would be when tension is equal to 0. Why? Well, we have two forces acting on our bucket, right? Gravity and tension. At the top, the minimum speed is when tension is 0 because we are relying on gravity to provide enough centripetal acceleration to keep our bucket moving. I'll make this more clear. The minimum speed needed to keep the bucket moving and to keep the water inside the bucket is when we're going fast enough where the force of gravity is providing enough centripetal force to keep it moving. Let me try and visualize for you what's happening at this moment in time. If the bucket is too slow, the water will spill out. And at this moment, the only force acting on it would be gravity. So if gravity is enough, the bucket will barely make it over, and any slower, it will fall straight down, and water will spill on the child's head. That's the minimum speed we need, just to barely push it over with only gravity. So let's find the net force in the radial direction, so toward the center. Right here, we have the net force as gravity. We're not considering tension because remember, tension is 0. Gravity is the centripetal force, and the centripetal force formula is mv²/r. This equation means that gravity is equal to the centripetal force, which means that gravity is keeping us spinning. We can cancel out mass for g equals v²/r. We're looking for the minimum speed at the top, so let's solve for velocity. When you solve for velocity and you rearrange the equation, you get v equals root gr, which is equal to the root of 9.8 times 2.3. Remember, 2.3 is the radius. Then you get roughly 4.75 meters per second. That's the minimum speed your bucket needs to be traveling at for it to not spill water at the top. Now let's ask a second question to expand on this and keep learning. Now take this position at the bottom of the path. If we assume that swinging the bucket down here is twice as fast as the velocity at the top, then what is the tension of the handle? Okay, well first, let's find how fast it's going. We know it's 2 times faster than at the top. And at the top, as we just solved, is 4.75 meters per second. That means velocity at the bottom, which we'll label with b, is 9.5 meters per second. Okay, that's useful. Now we can find the force of tension. Let's consider the net forces acting on this and apply Newton's second law. So F equals ma. The net forces acting on the bucket at the bottom is the tension pulling it up and gravity pulling it down. So subtraction. Now these forces, that is the centripetal force of the bucket. So we can write mv squared over r. I'm going to go ahead and solve this for tension now. There we go, there's our answer. So here's a little tip when it comes to solving physics problems in general. Break it down into parts. You don't have to solve it all at once. Anyway, here's our answer. So at the bottom, the tension of the handle is this, 36.8 newtons. For every topic I cover, I like to create a free cheat sheet, and I use them myself as well. So if you want your own with all the formulas you'll ever need in one place, then go sign up in the description.